Hello everyone. For my independent lab, I wanted to look at the effects of inlet temperature on the cooling ability of radiators. The idea for this came from playing on my own computer. The room I was in would get warm over time. Led me to the idea that the computer was putting off heat, then it was getting pulled back through the intakes, and thus just continually reheating the same air. Given that this is a kind of like a feedback problem, I was curious if the radiator's efficiency changed with the inlet temperature, if the air itself could only take so many or so much heat per pass, or if the heat transfer rate remained the same, it's just the temperature of everything rose by some amount. This is what I drew up for my idea behind the experiment before I started putting everything together. I would have a temperature probe in the intake airstream, a temperature probe physically touching the radiator fins, and another temperature probe in the exhaust airstream. I would put a constant load on the radiator, and I would change the intake air temperature between a high intake air temperature and a low intake air temperature, kind of just simplifying the process. The equipment I used for this was a LabQuest, 3 surface temperature sensors, the radiator, a way of putting a load on the radiator, and a way of changing the inlet air temperature. The procedure for this was setting up the LabQuest with the 3 surface temperature probes in the depicted locations. I decided to do a 1 sample per second rate for 2.5 hours. I ran a synthetic CPU stress test, Cinebench R23, and that was my heat load on the radiator itself. I ran a repeating GPU synthetic stress test, 3D Marks TimeSpy Extreme. This set the high intake air temperature. Logged the temperatures until a steady state was reached. Stopped the GPU stress test, continued logging until a cool steady state was reached. Saved everything, shut it all down, disassembled, and put all the equipment away. This is the data that was collected. I'd like to point out a few things to start with. Right here we have a drop in temperature where the computer tests had to be restarted, which allowed everything to cool off. Our next big drop here, and this one here, was due to computer crashes due to temperature. And this final dip here was again restarting the CPU stress test. I'd like to point out these 2 points, basically at the top of the radiator and exhaust temperatures. You can see that the delta between the two is larger as it kind of steadies out at these high temperatures as compared to almost anything over here at the low temperature tests. This is a graph of intake versus exhaust air temperatures. Right here between the 15-minute and the half-hour mark, and right here, right before the 45-minute mark, those were our high temperature tests. And you can see that those were on average 1 degree higher than our low temperature test section, which I took from the 1 hour 45-minute mark. This is a radiator temperature versus exhaust temperature tests. Again, right before the half-hour mark and right before the 45-minute mark is where we're looking at the high temperature tests. Comparing that over here to the hour and 45-minute mark, you can see it's a substantial difference in temperature between the radiator and exhaust. Well, the difference between the 2 temperatures. is noticeable. The uncertainty in the sensors that I used was plus or minus 0.2 degrees Celsius with an advertised resolution of 0.03 degrees Celsius. We covered the 2 stress tests, spot resetting, and the 2 times we had computer crashes. My conclusion on all this data is that there is a clear separation of radiator and exhaust temperatures in the high heat test that does not appear in the low temperature testing. I interpreted this as the radiator's ability to dump heat into the passing air is diminishing as inlet temperatures rise. While there are indications that the radiator does not perform as well at higher inlet temperatures, it would require more testing with a more robust setup to further increase the inlet air temperature and exaggerate the efficiency losses at higher temperatures. Thank you for listening, and this was my independent lab.